welcome back to another episode of Planet Hunters Coffee Chat. I'm your host, Cassie Prolongo, and of course, joining me as always, Nora Eisner. Good to see you, Nora.
Good to see you, Cassie. How are you?
I'm very well, thank you. I have my lovely cup of tea today, so I am ready to go. I have hibiscus tea this morning. It's all right. It's not as good as maybe your British tea, baby, but it's okay. It's not too bad.
I'm drinking Swiss herbal tea today, so
Mm.
imported from Switzerland. It's fantastic.
Oh, very nice. I love it. Awesome. Well, I know I say this a lot, but I am very excited about today's episode. And I do say it a lot because this stuff really does excite me. This is going to be a callback to way back to our first or second episode. You may remember or may not. It's okay. I won't judge you if you don't remember. And one of the things that I talked about was that I was hoping to see this series grow and change and evolve and expand. A lot of ease there. And the reason behind that, because exoplanet stuff is super fun. It's a lot of cool stuff, but there's other things out there. We've got some other cool things that we can talk about. So I'm really pleased to say that based on a recent paper that some of you might have seen that Nora and her contributors published, we're going to kick off a nice series about stars. And we're going to be joined by stellar experts. So that is something that I'm very pleased about. I'm very excited about. I'm sure you're excited to do this too, Nora. And yeah, it's going to be really cool.
Yes, this paper has been in the making for so long. I'm just glad it's finally out there in the world and people can see it. I've also been talking about the system for so long. Once I mentioned the TIC ID, you might notice that this is one of the 2 TIC IDs that I've memorized. And the reason why I've memorized it is because I've been working on this system for about 2 years. This is a pre-pandemic system. I've just read that number so many times that it stuck.
And eventually you're going to get it tattooed on your wrist and everything, right? And so,
yeah, along with the other number of the other system that I've memorized.
So if you didn't see it go out on social media, we're going to make sure that we have the link included on here, but it did go out on social media. I will read the name of the paper as well. It's called Planet Hunters TESS 4, a massive, compact, hierarchical triple star system, TIC ID 4707. 10327. A lot of sevens, so it's quite a lucky one, I think.
Yeah,
so good. Yeah.
All of the ones that I've looked into deeper have had quite nice TIC IDs. So hopefully we can keep going with that trend. Otherwise, I can't ever remember them. So they just need to have that nice TIC ID.
So even though we're deviating a little bit from exoplanets, we hope that this is going to be something that you guys enjoy. So even though that we're starting something different, it's the origin story, very much like a comic book series. The origin story had a very similar making, and it all started with you, citizen scientists, and more specifically in the talk forum. So I thought, Nora, we could take it back and you could talk a little bit about the origin story for this.
Yeah, so the system was, like you said, it was flagged on the talk discussion forums, and it was flagged because there are multiple periodic signals in the TESS light curve. So there's an eclipsing binary, so we see nice, big, deep eclipses. But in addition to seeing those nice, big, deep eclipses from one star going around another star, we see additional dips. So that was flagged on the discussion forum, and I saw it and I was like, that's one that I want to look into. It looks very interesting. So I did look into it. And I think today we will look at the TESS data for this target. We will look at why it was flagged. I will show you these signals. And then in future episodes, once we've looked at the TESS data and all the information that the TESS data can give us, we will look at kind of the next step of the journey of the system and how we continue to look into it, and how we kind of came to these conclusions as to why it's really interesting and why this is a unique system. So before we jump into that, I will give the headline of why the system is interesting. The system is interesting because it has 3 massive stars orbiting around one another. So triple systems, or that's what we call them. If there's 3 stars, they are triple systems, triple star systems. They are not rare. There are lots of binary systems out there. There are lots of triple systems in the universe, in our galaxy. There are also higher order multiples, so 4 or even 5 stars going around one another. But this one is very interesting because all of the 3 stars that we see are very, very big, and they're very close to one another. So the time that it takes those stars to go around one another is quite short, and that has very important implications for how this system could have formed and what will happen to the system in the future. So before we go into how we found that out, how we know all these different things, and dive deeper into why it's interesting, we will start at the beginning and start with the TESS data and what that tells us. So I will
Nice kickoff, Nora. I love it. That's a great way to, yeah, because, and if you haven't, you know what, and I want to just put, I do this a lot, a little caveat out there. If you haven't read an academic paper before, don't feel bad, because academic papers are written in such a way that's very difficult to go through. So just try your best at least reading some of the beginning parts of it, and then reading maybe some of the middle and some of the end, and think of some question. All right, let's get into this. So the light curve, TIC ID.
4707103227. God.
Woohoo!
Memorize that one.
She's got it.
Never mind that it's on my screen. No, I do know this one. All right. So I think today we'll look at the TESS data, and we will cover some things that we've already covered, and we'll cover some new things. But like we always start, well, like we've so often started these notebooks, we started them off by importing the data using light curve. So hopefully this looks familiar here. So here we have the TIC ID. We've defined that here. We're importing it with light curve, and we're importing it for sector 17, 18, and 24. So those are the only 3 sectors in which this target was observed. And of course, then we plot it, because that tells us what the light curve looks like, and that's exactly what we want to know right now. So this is what would have been shown on the something that looks like this would have been shown on the discussion forums. So if we zoom in, okay, here. So here we can see kind of a more zoomed in version of this light curve. And as you can hopefully see, we have an eclipsing binary. So that's shown by these slightly shallower dips here. So we have the primary eclipses are the slightly deeper ones, and the secondary eclipses are the slightly shallower ones. And in addition to that very, very regular binary or eclipsing binary, we have more eclipses, and those happen around every 9.9 days, whereas that smaller, or those other eclipses, happen around every 1.1 days. So we have multiple signals in this TESS light curve, and those are important because these are the reason why I continue to look into this system a little bit more. Now, something that I'm not sure if I've mentioned before, but if I haven't, I'll mention it now, is that especially in the TESS data, blends are really common. So a blend is when you have multiple eclipsing binaries just that happen to be close to one another on the sky. They don't have to be close to one another physically, but when we see them as kind of a 2D projection of where they are located in space, they just happen to be somewhat close to one another. So just because we see multiple signals in data doesn't mean that they are physically associated with one another. So one thing that I always check is I look at the orbital periods of signals seen in TESS data, because if those signals are multiples of one another, that could be an indication that they are part of the same system. So for example, if we have something that goes around a star every 1 day, and then we have another signal that is every 10 days, then we call that a resonance. So they are in resonance with one another. Every time that this one goes around exactly 10 times, the outer one goes around exactly 1 time. And that can be a very good indication of those being kind of bound to one another and part of the same system. So that is something that I looked at in this system. I looked at those orbital periods, and I found them to be 1.1 day and 9.9 days. So very, very close to being in a 9-to-1 resonance. So that is why I continue to look at the system.
I was going to say that your alarm bells must have been going off at that point, where you were like, ooh, okay, what's happening here?
They definitely did. All right. So if we run this next cell here, here is just those 2 signals plotted next to one another. So we have that 1.1 day binary that we see here. We see that nice primary eclipse that's slightly deeper, and on the side, each half kind of see part of it on each side, we have that secondary eclipse, which is slightly shallower. And this one is phase folded on that 9.9 day signal. But the problem is, like, as you can see on that right there, it's very difficult to line all of those up, because that 1.1 day signal is getting in our way. It makes it very difficult to see what is happening. So the next step that we do when we have a scenario like this is we try to remove that dominant signal, that 1.1 day signal. We want to get rid of that from the light curve. So we will go through how to do that next. All right. So we're just going to scroll through some code, which we don't need to worry about. We just need to run it. And we will run it. So here's some code that does this for us, that removes that 1.1 day signal. So kind of very briefly, what we do is we phase fold on that period of that 1.1 day period. So we phase fold it just like we have here. That's the kind of the black data. We first mask out that 9.9 day signal that's now shown in gray. We want to remove that from our model. And then once we phase fold it very nicely, with that signal removed, then we make a model of what that 1.1 day signal looks like. And that's that orange line that we see going through there. So this is our model of that 1.1 day signal. Does that make sense?
It does make sense. That's fantastic. It reminds me a little bit, it's like Photoshop a little bit when you kind of, get mask cut anyway, but that's really cool. So you can see it very clearly then, and you remove that completely. Did you write the code for this, or did somebody else? Yeah.
Cole wrote this code.
That's cool. I love that. It's a good, it's the dream team working together once again.
Well, he's second author on the paper. It's good that it was important for him to contribute.
And it's good. And that's, once again, science does not happen in isolation. It's usually a team effort to get these things to come across. Okay, great. So then you got that. It's very clear. So then what was the next step after this that you went on?
Okay, so we have this model, and the next step is that we remove that signal. So if you think back, before we do that, if you think back to, we've now removed this 1.1 day signal from the thing on the right, from the light curve. So we're expecting to now just see that 9.9 day signal, nice and clear, sticking out, very obvious. So let's go down and see whether that is what we see. Cool. Okay, so this is what we have left over once we removed that 1.1 day signal. And what's immediately obvious is that we do see that 9.9 day signal. Those are those really deep eclipses that we see. They're very, very obvious now. They were less obvious before, but they're very obvious now. But what's really interesting about this is that in addition to seeing that 9.9 day signal, we also see another signal up here. So I'll zoom in on that a little bit so that we can see that.
And that was not something you were expecting to see.
No, so with that 1.1 day signal there, we couldn't see this at all. So this came as quite a surprise when we saw this once we'd removed that 1.1 day signal. So you can see here, the things that go beyond the screen, because we've zoomed in, those are the 9.9 day eclipses, and we're left with something with a period of around 4 days, which we weren't expecting to see. So what we now have is we have 3 periodic signals, and we don't know how they're linked. We were very confused at this point. I'm still slightly confused. So we now have that 4.4 day signal. You don't have to take my word at it, but that is what it is. We can phase fold on that 4.1 day signal, and there we see it nice and clear.
Wow.
So to really look at all those signals, we will plot them all next to each other just so we can compare them. And we can see we have the very deep 1.1 day signal, the slightly shallower 9.97 day signal. So the reason why it appeared deeper in that first kind of light curve that we looked at is because this signal always overlapped with the 1.1 day signal, and it overlapped and was a kind of a linear addition of one another. So you just add each data point on top of the other data point, which is kind of what we had before. And then we have the very shallow 4.1 day signal. And because it's so shallow, you can see how shallow it is compared to the other eclipses. That's why it was so difficult to see before we removed that 1.1 day dominant signal in that light curve.
So did you have an idea at this point of maybe what you were looking at? Or, I mean, obviously you still needed to do more data and get it more data and follow-ups, but did you have an idea of, oh, I think we're looking at something like a compact triple system? Or were you just like, I have no idea what this is yet, I need more data?
At this point, I had no idea what we're looking at. And at this point, we have no indication that we are looking at a hierarchical triple system yet. Wow. So slight spoiler alert, the 9.97 day signal and the 4.1 day signal are not part of the hierarchical triple system.
Oh. So that threw you a little bit because they were not part of this system.
Well, that's also something we didn't really know at this time. I'm not really sure what we knew at this time. Not very much. At this point, it was just a whole lot of confusion.
I think that's the process of science too. It's just a whole lot of confusion until, keep throwing out, okay, it can't be that, it can't be that. And you just keep digging, digging, digging until you find the buried treasure, basically.
Absolutely. Yeah. At this point, I'd almost written the system off as being not interesting. I was almost convinced that this was just a lot of blends and that was it. But the problem was that by this point, I had named the system. I give them nicknames. So I was very attached to it. So
you were invested in it. See, the thing when you start to name things, you were invested in it at that point. It was part of you.
It still is. Okay. So I didn't give up on the system, and I'm really glad I didn't, because it does get very interesting.
Yeah, perseverance that's part of what, exactly what you needed to do. Okay, so at this point, where did you have to go from here? Where were you like, okay, we don't know what it is, we need to get more data, there's might be a blend, may not be. What did you do at this point?
So that's an excellent question. So the next thing that we did as a team, is we looked at the timings of the eclipses of that 1.1 day signal. So if we think back to, and we did an episode on TTVs, so transit timing variations.
Yes.
So if that's what happens when you have planets and you have multiple planets and they perturb the orbits, or they gravitationally interact with one another, which causes the times of the transits to sometimes be early and sometimes late. Well, the same thing can happen with stars, but in stars we call it eclipse timing variation, so ETVs, but it's exactly the same phenomena. We have stars going around one another. We have a potentially third star or even more stars orbiting around the binary, commonly orbiting around one another, which causes the timings of those eclipses to vary, and sometimes be slightly early and sometimes be slightly late. I think by the time when I looked into this, I still thought that 9.9 day signal was orbiting around that binary. So I looked at the eclipse timing variations, expecting those timings of those eclipses to vary with a period of 9.97 days. I expected them to be always slightly early and sometimes late, again, with that 9.97 day trend. Mm-hmm. So I extracted those eclipse timing variations. The way I did that, we're not going to do it today, we're just going to skip to the results, but very briefly, the way I did that is I took a phase folded model of the 1.1 day signal. I fit a trapezoid to just the bottom of these eclipses. I made a best fit model. I then took that model that I generated and fit it to each one of the eclipses. And the only thing, the model had to stay exactly the same. The shape of that trapezoid had to stay exactly the same because the eclipses should look the same. But the only thing that was allowed to vary is the time of it. Right. So that could give me a very clear indication of the midpoint of those eclipses. And those would tell us whether there are eclipse timing variations. All right, so let's import that data that I'd already extracted and we'll plot that. Okay. So these are the observed times of the eclipses minus the calculated times of the eclipses. So what that means is we call this an O minus C curve. The calculated time of the eclipse is the time of the eclipse if that period were constant. So if, for example, the period in a hypothetical scenario, if the period were exactly 1, the calculated time would be 1, 2, 3, 4, 5. And the observed time would be, for example, when it's calculated to be 1, it might be 1.1. So that's kind of how we get to that O minus C curve. And what we can see is we can see eclipse timing variations, which is really exciting. We can see that those eclipses sometimes happen a little bit early and sometimes happen a little bit late, which is exactly what we wanted.
Fall out of your chair when you saw that?
Sorry?
Did you fall out of your chair when you saw that?
I was so happy. I was convinced I was doing something wrong.
That's so cool.
But you might notice that eclipse timing variation does not happen at a period of 9.97 days, which means that thing that is causing those eclipse timing variations is not that 9.97 day binary that we see in the TESS light curve.
It was something else. Something else was contributing to it. Oh, and so the shoveling continued, going down looking for what was happening here. So it brought up more questions. It answered some, but it brought up more questions at that point.
It made the system so much more confusing. So yeah, at this point we just had, so this is at a period of around 52 days. So at this point we have a 1.1 day binary, we
Right.
have a 9.97-day signal, a 4.1-day signal, and a 52-day signal. So we have 4 signals. So with just having that information, that could either be, what could that be? It could be 3 stars in binaries, just happen to be close to one another. It could be a triple system and a binary. It could be, I don't even know what else it could be. It can be a lot of things at that point. And it's with just the test data, we don't know what the system is.
Right. So
So
that's where at that point you needed to enlist the help of like the big guns and really get that support and that get furthering the more data. You needed to look beyond just the test data, didn't you, at that point to really see what was going on?
yes, so at this point we started observing the system from the ground, and we will cover what
Yes.
that information is and how we got to that information and what it tells us, I think, in the next episode. We'll keep you waiting
Perfect
more.
segue into our next. So I did say at the beginning that we're starting a series. Nora nailed it. Perfect segue into our next. So with our, we hope that you enjoyed this episode. It's a little to be continued with the dot 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 at the end. We are going to bring in our some other. We've got Nora, of course, here, but some other experts to talk about a lot of these other things. So stay tuned. More things to come. So we really encourage you guys to go ahead and have a look through this. You don't have to read the whole paper, but if you have questions or anything doesn't make sense, write some questions out on YouTube. You can also do it on our Twitter feed and stuff like that too. Have some questions because we're going to talk about more about this with our experts, but we want to have them, answer questions too. So I think we've had enough for today. Thank you so much, Nora. This was fantastic at the start of this journey, and I can't wait for us to talk with the upcoming experts. I'm being very vague about that, but that's okay. You'll see why in future episodes. So good to see you, Nora, and congratulations on the paper once again.
Oh, thank you.
Okay.
See you next week.
Okay, see you next week. Bye.